on your magic net, you need to swing to another state where it lets go of those. So in our case, what we use is we use acidity. We use a source of acidity to then release the particles. Now we have the magic net without the particles, without the CO2, and it's going to swing back to an alkaline state where it's ready to absorb CO2 again. And then back to a sour state. Bitter, sour, bitter, sour, bitter. Each one of those states, it absorbs or releases the pH swing is what you're doing when you bake a loaf of soda bread. We're just doing it on a great big scale. Those two magic elements were there in climate tech. It was extremely difficult and it was extremely important. You need an army of hardworking people to get that kind of a project done.
You're listening to Bite Size Climate Tech, Season 3.
Hi, Dr. Yoshi.
Hello, Lydia. Good to see you.
Good to see you again. Welcome to the show. Dr. Deóis Ua Cearnaigh is the co-founder and chief technology officer of Aeon Blue. He has 3 decades of experience in renewable energy science, ranging from biofuels to solar panels to fuel cells and wind turbines. And now you are dedicating your time in Aeon Blue.
Yeah, that's right. And for the last couple decades, I've been working in synthetic fuels and in carbon dioxide capture.
Which is why today we're going to talk about something that it's a fundamental concept behind your company's technology. It's pH swing.
pH swing is a method of DAC. It's a method of direct air capture. Swings give the idea that the system is sort of swinging from one place to another. And that could be like from hot to cold. That could be from bright to dark or dry to wet, maybe sweet to dry, like wine. And another one of these sort of opposite states is sour and bitter. So pH basically is just a fancy way to say sour and bitter. And you move from one state to the other because we've got substance that's in the air that we want to get out of the air. How do we do it? Well, we look at that substance and we say, what does it like to do? What does that carbon dioxide want to stick to? That's what we make our net out of. We make our net out of alkalinity, out of base. And carbon dioxide turns out to be an acid gas. So if I have a base, it will stick to that base. Now, all I need to do is I need to make that base release the CO2 somehow. Once you've caught these carbon dioxides on your magic net, you need to swing to another state where it lets go of those. So in our case, what we use is we use acidity. We use a source of acidity to then release the particles, which now we have the magic net without the particles, without the CO2, and it's going to swing back to an alkaline state where it's ready to absorb CO2 again. And then back to a sour state, bitter, sour, bitter, sour, bitter. And in each one of those states, it absorbs or releases the CO2 that it's captured.
Swing, as you mentioned earlier, is the opposite states. So there's people who are doing hot and cold. In your case, pH swing is the bitter and sour. In the lack of better analogy, that it's acidity and alkalinity. In the alkalinity states, you are capturing the CO2. In the acidity state, you're releasing.
Yes, that's exactly it. You have to be in one state where you can capture the CO2. So alkalinity captures CO2 because CO2 itself is what we call an acid gas. And that means it likes to react with bases. Acids like to react with bases. Bases like to react with acids. So if you have a base or an alkaline source, it grabs onto the CO2. And then to make it let go, you just make it sour. You expose it to some source of acidity, and then it releases the CO2. So that's really, it's the swing. Swings are how all separations work. There's some interaction that's favorable in one state, swing to the next, let it go, swing back to the right, go back and forth. They all work this way. It's the fundamental of separation science.
Alternating changes in the pH, the acidity and alkalinity that occur in a carbon capture cycle.
That's right.
In your very specific technology,
our particular chemistry actually co-produces acid, base, and hydrogen all at once. You get some synergies there because you need to spend a certain amount of energy to make some product, to make hydrogen. So we try to tack on all of these extra opportunities to make the co-products. Once you've got that acid in base, you can very easily design any system to swing from an alkaline system to do your carbon dioxide absorption into an acidic system to do your release. Once you've got the concentrated released CO2, you can then put that underground.
How would you explain this to an 8-year-old?
If you like Chinese cooking, you know that one of the methods of tenderizing meat is called velveting. You take the meat and you mix it with baking soda, and you let the baking soda marinate for an hour. Just that it changes the meat somehow. It makes the meat better. The meat is like the air and it's pulling CO2 out. And now you're ready to cook the meat, but it's bitter. It's got this baking soda in it. Nobody likes the taste of baking soda. So what do to get the baking soda flavor out? You give it a little twist of lemon. Baking soda reacts with the lemon, off comes CO2, as a matter of fact. And now what you have is this really tender, lovely meat, a brilliant flavor, and isn't tainted by the flavor of that baking soda. As close as you could possibly get to exactly what we're doing is we're actually using a source of acidity to neutralize baking soda. So another example that really is good is yogurt. You know, yogurt is a little sour. One of the methods of making your bread rise is you put baking soda in your bread, in your dough. Baking soda is alkaline. It's actually already got the CO2 in it, and it's bitter. And so if you've ever tasted baking soda, it doesn't taste very good. It tastes bitter. What people will do is, you have your flour and you add your baking soda and your salt and everything else, all of your other ingredients, you mix it up. And then the very last ingredient that you add is a great big dollop of yogurt. Knead that, and then it rises, starts to expand. So when you're baking and you make soda bread, how do you get the carbon dioxide to make the bread rise? Well, you add some source of acidity, so you can add yogurt. The use of yogurt to make that bread rise is very effective. And conceptually, it's the same thing that Aeon Blue does. We have this source of alkalinity. We use it to capture the CO2. And then we basically just make it sour so that it gives off the CO2 when we want it, where we want it to give off the CO2. Obviously, we want it to give off the CO2 in a way that we can capture it.
Oh, I see. Somebody else has explained this to me. You know, when you cut the slice of French baguette, then you see those bubbles. That's the CO2 is released. Finally, the yogurt just make the CO2 that it has captured to release. So then that's why eventually you have those bubbles in the sourdough bread.
pH swing is what you're doing when you bake a loaf of soda bread, is you're doing pH swing. We're just doing it on a great big scale.
Okay, so the next segment is you have 2 questions from previous 2 guests.
Jackpot.
The first one is, how would you build greater collaboration between different carbon dioxide removal pathways?
I think that most of the carbon dioxide removal pathways that we have are already really pretty synergistic. We use pH, for instance. Inescapable anytime you have a big machine, there's going to be some heat generated. And someone like TerraFixing, our colleagues over there, they need that low-grade waste heat for their CDR process to work. We have what they need, and we don't need it. We want to get rid of it, in fact. Here's another one. Most of us, we all use charcoal. Charcoal is necessary to clean things, useful in cleaning gases and liquids and stuff like that. We can all get that charcoal from biochar. I think that the ways in which CDR pathways are already synergistic is huge. We just need to work together. We all have a lot of synergy. And I think that we have a really good, healthy community likes to work together.
So the second question is, name 2 to 3 missing links to truly decarbonize the world.
First one that I would say is we need fusion and fast breeder reactors, a large amount of very cheap energy. This is an energy hungry process. It costs energy to separate those things. That energy has to come from somewhere. We need to have the energy infrastructure to drive it. And I think that actually dovetails into the second point, which is we need to have a global recognition of seeing how important CDR is to our global community, how important it is for all of us to get behind CDR. And as the IPCC report says, all pathways to stop global warming require CDR. And we need that knowledge to be widespread, along with the knowledge that means we need to have energy We need that low carbon, zero carbon energy so that we can make it carbon negative. If we don't have the turbines, if we don't have the solar panels, if we don't have the breeder reactors, we can't do it because you're just burning fossil fuels to capture fossil fuel, which doesn't make sense, right? And that means new construction. And that means we all need to be on the same page. Yeah. Cheap, renewable
cheaper energy, and then
getting permitted.
You can leave a question for the next guest.
How can people in direct air capture best communicate with you? What methods and what tools would be better for us to communicate with our allies in climate tech?
Why did you decide to work in climate?
I was at university. I was picking a problem that would inspire me. I wanted to pick something that affected me and my family and my community. In my earliest youth, I chose food because we all needed to eat, and this was a way that I could communicate and connect with my family. And then I thought about medicine because obviously I'm a human being, and I wanted to be able to help others. I landed on energy, ultimately on CDR, because I realized that in my studies that if we did not solve that problem, all of the food and all of the medicine and all of the everything else was not going to matter because we weren't going to be able to do any of it. It hit me after years of study as the most important problem that we could possibly attack. And those two magic elements were there in climate tech. It was extremely difficult and it was extremely important. You need an army of hardworking people to get that kind of a project done. I signed up for the intellectual army to solve the crisis of the 21st century. And aren't we all looking for something inspiring and challenging to do with our lives? And meaningful, inspiring, challenging, and meaningful. And, you know, what could be more challenging than changing the global energy structure, the global energy system? And what could be more meaningful than saving the environment that we all live in? You know, and there are many approaches to do that, and I took them. I worked many years in renewable energy and nuclear energy, but here we are. We need CDR, and without it, we can't survive. Let's make climate cool again.
Climate cool again. Let's make climate cool again. Thank you so much for coming to